Okay, so it's time. So let's get started. Today's discussion seminar. So hello everyone. Thanks for joining Rocky World's discussion today. And this is gonna be our second meeting of this year. And I am Hiro Kurokawa. I'm moderator for today. And so it is my pleasure to introduce today's speaker, Sekine. Yes, could you turn on? Yeah, oh, perfect. So Yas is a professor as well as a director of the Earth Life Science Institute, ELSI, at Tokyo Tech. And he is an expert of the experimental studies and numerical modeling of the various solar system environments, such as the icy world and early Earth and early Mars. So today he is going to introduce his recent work on the icy satellite Enceladus and discuss its implication on the chemical evolution toward life on Earth. And as our discussion format, we have, as usual, 30 to 40 minutes talk by our speaker, followed by a plenum discussion. And I would like to ask participant to use your full name on the Zoom name so that we can identify who you are. And also please keep your mic muted, and only when you speak, please turn on your mic and the video. So let's move on to Yas' talk. So Yas, could you share your screen and start presentation? Thank you.
Yes, thank you, Hiro, and thank you everyone for joining us today. I'm Yasu Sekine, ELSI at Tokyo Tech. So today I'm going to talk about our finding of phosphate in Enceladus ocean. A enormous concentration of phosphate has been found in Enceladus ocean. And also I'd like to discuss with you about the chemical evolution toward life on Mars, from these aspects observation, based on this observation on Enceladus. So we have many collaborators. Some of the members are Cassini mission members, and others are my collaborator in the Japan team to interpret the observation by the Cassini spacecraft. So is there life beyond the Earth in the solar system? So this is a really powerful and a fundamental question. And the planetary scientists, geochemists, organic chemists, and the life scientists may need to consider seriously about this question in the next decades. Liquid water, chemical energy, and organic matters are ingredients for life, building materials of life on Earth. And according to whenever these three factors exist in any environment on Earth, there is always life. And according to the recent advances in the spacecraft explorations, we now know that there are multiple planetary bodies in the solar system that have or had in the past these three factors on the surface or in the subsurface. So I see ocean worlds like Saturn's moon, Enceladus, Titan, and Jupiter's moon, Europa, and Ganymede have attracted the many attention, not only from planetary scientists, but also from public audience because of the presence of liquid water, subsurface ocean, beneath the icy crust. For a long time, until the Cassini spacecraft, Cassini observation, however, the chemical composition of the subsurface oceans, the availability of chemical energy, and the organic matter remained unclear. However, this situation has totally changed due to the Cassini missions. So NASA's Cassini spacecraft found the water-rich materials erupting from the Saturn's moon Enceladus subsurface ocean. By correcting the plume materials through the flyby, the Cassini has revealed the chemical composition of the subsurface ocean. So the subsurface ocean of Enceladus contains the dissolved CO2, hydrogen, ammonia, methane, complex organic materials, sodium salts, and silica. So where these hydrogen and the silica came from? So this hydrogen and the silica was produced in hydrothermal system in which the rock materials, chondritic rock materials, and high temperature water interact each other in between at the interface between the subsurface ocean and the chondritic rocky core of Enceladus. So the combination of CO2 oxidant and hydrogen reductant, there is a chemical energy available for methanogenic life in Enceladus. And considering the concentration of CO2 and hydrogen and available chemical energy, the chemical energy available within Enceladus is almost comparable to hydrothermal vents on Earth. So in other words, if we put the Earth's methanogen into Enceladus ocean, those methanogen can survive there by obtaining energy. So Enceladus is habitable in terms of the availability of liquid water, chemical energy, and complex organic materials. But what about nutrients? The nutrients include the phosphate. Especially the phosphate is one of the most important nutrients for Earth's life because it plays many roles in biochemistry, like forming DNA, RNA, and ATP. So because the phosphate play many roles in biochemistry, and also phosphate is always low abundance in Earth's aqueous environment. The availability of phosphate has controlled the primary bioproductivity in Earth's ocean throughout its history. Despite the importance of phosphate, the availability of phosphate in Enceladus ocean and other ocean worlds is largely unknown and under debate. Some previous study suggested that the phosphate concentration should be very low in icy ocean worlds because on Earth, the phosphate concentration usually occurs in the drying evaporation cycle on the surface of land. So in the icy ocean world, in the subsurface ocean, there is no land and there is no atmosphere. So it's really hard to concentrate the phosphate in aqueous environment in the deep ocean icy world. However, there is no observational constraint that directly determine the phosphate concentration in the ocean world. So to summarize first my talk, we report the first finding of phosphate in Enceladus ocean. In particular, we found anomalous enrichment of phosphate in Enceladus ocean based on Cassini observations. The estimated phosphate concentration around 10 millimolar in Enceladus ocean is about more than 1,000 times that of typical Earth's oceanic water. So then, based on the geochemical experiment and the modeling, we interpret this enrichment occurs due to the moderately alkaline pH and the CO2-rich environments of Enceladus. So, given this aqueous environment of alkaline pH and CO2-rich conditions that commonly occur in the icy ocean worlds beyond the CO2 snow line in the solar system, like a Triton, Pluto, Ceres, and the uranium moons, that these icy bodies would commonly contain high concentration of phosphate in the subsurface ocean. So this is the summary and the take home of my talk. So let's go through the detail of my talk. So the detection of phosphate in Enceladus ocean was done with Cassini cosmic dust analyzer, which is a time-of-flight mass spectrometer onboarded on the Cassini spacecraft. In this study, we used and analyzed we used the data set of the mass spectra of individual particles of Saturn's E-ring. The Saturn's E-ring is a very tenuous ring surrounding the Saturn. And in the center of the Saturn's E-ring, there is Enceladus. And it is well known that the Enceladus plume materials are source of Saturn's E-ring materials, because some of the plume materials erupting from Enceladus exceed the escape velocity of Enceladus and form the tenuous Saturn's E-ring. So the Cassini fibers the Saturn's E-ring and collect the E-ring icy materials and through the flyby and analyze its chemical composition using the time-of-flight mass spectrometer Cassini cosmic dust analyzer, or CDA. So according to the previous study, we found roughly 3 types of particle of Saturn's E-ring, type 1, 2, and 3. And among these 3 types, the type 3 particle is sodium salt-rich particle. And the previous study shows that these type 3 particle, sodium salt-rich particle, directly derived from Enceladus ocean. So in the subsurface ocean, the liquid salt-containing ocean from the small droplets of seawater. And these droplets are frozen during the transportation to the space. And these ice particles contain the salt materials derived from the Enceladus ocean. So we call this particle type as type 3 particle. So my colleague Frank Postberg is one of the PI of CDA, Cassini CDA, and he and his colleagues has analyzed the many data set of the mass spectra of individual particle of type 3 particle during and even after the termination of Cassini missions. And his team, based on the analysis of the many spectral data of the salt-rich type 3 particles, we found some subtypes of type 3 particles with different chemical compositions. The left-hand side figure shows the typical mass spectra of major sodium salt-rich type 3 particles containing the sodium chloride and the sodium carbonate. You can see the peaks due to the sodium and the chlorine and the sodium carbonate. So this is a major type of type 3 particle. And based on the analysis of this particle, the previous study already constrained the sodium concentration in Enceladus ocean and also pH of Enceladus ocean as around 10. So on the other hand, the right-hand side figure shows the mass spectra of our newly found subgroup of type 3 particle enriched in sodium phosphate So you can see the peaks of phosphate-bearing sodium materials and subgroup in this subgroup of type 3 particle. So the fraction of this phosphate-rich particle is about 3% relative to all type 3 particle. So based on this fraction, together with previously estimated sodium concentration in Enceladus ocean, we can estimate the phosphate concentration in Enceladus at around 1 to 20 millimolar level. So this concentration of phosphate in Enceladus is about 1,000 times that of Earth's oceanic water. So typical Earth's oceanic water contained about 500 nanomolar of phosphate. So to understand the factors that control the anomalous enrichment of phosphate, we performed the laboratory experiment and the modeling of water-rich interaction simulating Enceladus seafloor. So this is the schematic illustration of our laboratory experiments in which we introduced the carbonaceous chondrite powder starting materials as analog of Enceladus rock, together with sodium bicarbonate ammonia solution as an analog of Enceladus seawater, based on the previous observation of Enceladus water by Cassini. And using the flexible gold tube reaction cell and also autoclave system, that we can increase the pressure and temperature of the starting materials to 150 degrees Celsius and 300 bars. This pressure is almost comparable to the rocky core of Enceladus. And this temperature may be too high for Enceladus, but this elevated temperature allows us to study the factors that control the phosphate concentration in Enceladus on the time scale accessible in the laboratory experiments. So during the experiment, we can collect the fluid sample during the experiment, and also after the experiment, we collect the rock materials and do the mineralogical and the chemical analysis for the rock component. So this figure shows our experimental results of the relationship between the total carbonate concentration on the horizontal axis as a function of total phosphate concentration in fluid materials, fluid samples during the experiment. The numbers attached to the experimental data show the in-situ pH value. So we control the in-situ pH value around 10, based on the Cassini observation for Enceladus ocean. So you can see a clear positive correlation between the total carbonate concentration and the phosphate concentration in the fluid sample. So this means that if you have more CO2 in the fluids, you can get more phosphate in the fluid materials. And rock residues collected after the experiment, that we found the presence of carbonates, calcium carbonate like calcite, and also calcium phosphate like apatite in the rock samples. So based on the experimental results of the findings of apatite, calcium phosphate, and the calcium carbonate in the rock materials, we consider that the phosphate concentration in the fluid would be controlled by the mineral buffer system between the apatite and the calcite. So in this equation, you can see the apatite plus the dissolved carbonates is going to be the calcite and the dissolved phosphate. So the equilibrium constant of this reaction can be written as follows. So equilibrium constant is almost equal to this value. So if you can determine the pressure, temperature, and pH, then the phosphate concentration can be written as a function of total carbonate concentration. So in the experiment, we set the pressure as 300 bars and the temperature is around 150 degrees Celsius. Then the pH is already measured. So we can theoretically calculate the concentration of phosphate and the total carbonate if this chemical reaction determine the both of these concentration. So these figures show the calculation results of phosphate concentration determined by this equilibrium calculation as a solid line superposed on the experimental data. So dotted line in this figure show the different type of phosphate and the carbonate mineral buffer system. So comparing these two, you can see that the measured phosphate concentration is generally in good agreement with the apatite and the calcite buffer system. So in other words, and if you have any increase in delta CO2, so if you have any increase in the CO2, then the reaction go to the right-hand side and form a more carbonate, and you can get more dissolved phosphate in the apatite phase. So an increase in the sigma CO2 leads to dissolution of apatite to form the stable carbonate, releasing dissolved phosphate to the fluid. So this relationship explained why you have more phosphate in the high CO2 concentration fluid. So this figure shows the assuming this equilibrium, then we can calculate the phosphate concentration in Enceladus ocean if we introduce the temperature, pressure, and the pH condition. So this figure shows the calculation result of the relationship between the phosphate concentration and the carbonate concentration according to the apatite calcite buffer system at 0.1 degrees Celsius and 80 bar pressure. The 80 bar pressure is almost comparable to the interface between the subsurface ocean and the Enceladus rocky core, and the 0.0 degrees Celsius mean that the Enceladus core's sea floor control the phosphate concentration in the Enceladus ocean. So this temperature and the pressure condition, you can see the relationship between the phosphate concentration and CO2 for different pH conditions proposed for Enceladus ocean. So the measured level of phosphate concentration by Cassini cosmic dust analyzer is consistent with previously constrained pH range and proposed carbonate concentration in the ocean. So this figure shows that the anomalous enrichment of phosphate in Enceladus can be explained by abiotic water rock reaction, namely the calcite phosphate and the calcite carbonate buffer system. So you can get the almost 10 millimolar level of phosphate if you have around 0.1 molar of CO2 for weakly alkaline condition. So finally, we would like to discuss some implication for comparative phosphate chemistry in the solar system. So the given common occurrence of apatite and the calcite in the water rock reaction in the solar system, that we can assume that this mineral buffer system is applicable to other ocean worlds in the solar system. So this figure shows the sensitivity of phosphate concentration as a function of pH for different carbonate concentrations. The red line shows the results for high carbonate concentration, like a sigma CO2 is about 0.2 molar level. So this level of CO2 can be achieved in the subsurface ocean if the icy body is formed beyond the CO2 snowline. So if the materials formed beyond the CO2 snowline, the building materials should contain a lot of CO2, and the abundance of CO2 is about this. So this red line shows the results for the ocean world beyond the CO2 snowline. On the other hand, the purple line shows the results for the ocean world inside the CO2 snowline. So due to the lack of CO2 ice in the building materials, the sigma CO2 in the ocean should be low for this body. So these two lines would correspond to the surface water and the thick atmospheric CO2 for red line, and also the low atmospheric CO2 for purple line. So in the previous study, the pH value for the subsurface ocean in Enceladus and other icy body beyond the CO2 snowline would be around 9 to 10 due to the high concentration of CO2. So in other words, the carbonates make the pH of solution around weakly alkaline. On the other hand, the previous study of geochemical model shows that the pH value for icy body inside the CO2 snowline become highly alkaline due to the abundance of ultramafic rocks and the rock components. So due to the abundance of CO2 in the subsurface ocean, the pH becomes weakly alkaline compared to these two. So you can see a large contrast in the phosphate concentration in the subsurface ocean across the CO2 snowline. So the phosphate concentration is more than 4 orders of magnitude higher in the ocean world beyond the CO2 snowline. So if we plot the phosphate concentration for RE Mars or Archean Earth, the value should be around here. So for RE Mars and the Archean Earth, we don't know the exact CO2 level, but the thick atmospheric CO2 is required to keep the surface temperature higher than the freezing point of liquid water. So the phosphate concentration will be around the 0.1 to 1 millimolar for RE Mars if the surface water is around, surface water pH is around 6 to 9. And for Archean Earth, the phosphate concentration can be 0.01 to 0.1 if pH of surface water is around 6 due to the thick CO2 atmosphere. So by comparing these oceans, subsurface ocean and surface ocean on the rocky world and the icy world, that we can say that the Enceladus and the icy body beyond the CO2 snowline should have optimal concentration of phosphate. So such a high phosphate concentration by alkaline pH and high CO2 concentration in the ocean can be supported by the presence of sodium phosphate mineral in the return sample from the asteroid Ryugu, originated from the beyond the CO2 snow line. So sodium phosphate concentration, sodium phosphate has high solubility. So the presence of this mineral qualitatively suggests the very high phosphate concentration in the pore water of asteroid Ryugu. So such a difference in availability of phosphates should affect the chemical evolution in those aqueous environments. And chemical evolution should be controlled by the availability of elements on the planetary body. The one good example is a recent finding of organic matter on Mars. The Curiosity rover has found the organic materials within the sedimentary rock of Gale crater. And according to the analysis, organic analysis of such a sedimentary rock, the Curiosity found some of the organic matter within the Gale sediment contain a high concentration of sulfur. So sulfur over carbon ratio is around 0.1, which is much higher than Earth's organic materials. So this could be due to the high availability of sulfur or sulfate in aqueous environment on Mars. So organic chemical evolution should be controlled by the availability of elements. So what about Earth's life and phosphate? So why does Earth's life use phosphate in DNA, RNA, or in ATP? And how did it all begin? So one possibility is that Earth's life might have emerged in a phosphate-rich environment on Earth. So on the current Earth seawater or in surface water, any surface water, the phosphate concentration is really low. So usually the phosphate is a limiting factor of bioproductivity. However, on early Mars, Hadean Earth, life may have emerged in the phosphate-rich concentration, so that the life used the phosphate as an important nutrient. According to the some chemical study, prebiotic chemistry, the high concentration of phosphate can catalyze some key reactions for nucleotide formation. So high concentration of phosphate is important to form the life-building materials. And also the phosphate can be incorporated into the organic materials, like forming the nucleotide via wet-dry cycles. So according to the recent knowledge of the chemical evolution, prebiotic chemistry, the high concentration of phosphate, like higher than tens of millimolar level, and also wet-dry cycles are required. So how to achieve this high concentration of phosphate and also wet-dry cycle on surface of Hadean Earth or Hadean Mars or very early Mars? So going to back this diagram showing the relationship between the phosphate concentration and the pH determined by the calcite and the apatite buffer system. The early Mars and the Hadean Earth concentration should be on the red curve. The red curve shows the results for the high CO2 concentration in the ocean. So according to the prebiotic chemistry, we need more than 10 millimolar level, so higher than this level. So unfortunately, for early Mars or Hadean Earth concentration is 3 to 4 the magnitude lower than this level. So in order to achieve this level, we need the alkaline water on the surface. So how to achieve such a alkaline water on Hadean Earth or primitive Mars? So one possible candidate of water that can achieve such a high concentration of phosphate is the pH of groundwater hosted by the deep crust ultramafic rocks. And the deep crust materials contain ultramafic rocks like olivine or pyroxene. So if the groundwater interacted with those ultramafic rocks in the deep crust, then the pH becomes alkaline condition. And then we can have the 10 millimolar level of phosphate in the water. And if we get such, if we have such a phosphate concentration, and then if we have a drying cycle for this water, such an environment could have both high concentration of phosphate and a wet dry cycle, where the nucleotide formation could promote. So one possible aqueous environment where the groundwater hosted by deep crust mafic rocks can be evaporated, and the surface is like a deep crater environment. So in a deep crater, the cratering excavate the crust, and the deep crust ultramafic mineral can appear on the surface. And if groundwater or surface water interacted within this deep crater, then the water could be, the pH of this groundwater or surface water will be alkaline, would be alkaline, like a pH around 10. So such a water is suitable for nucleotide formation, and also incorporation of phosphate into organic materials through wet and dry cycle. So based on the Cassini insight, we propose that the upwelling of groundwater within a deep crater could be one of the appropriate location for the phosphate-rich environment on rocky planet. So this is the conclusion, and we found enormous enrichment of phosphate concentration up to 20 millimolar level in Enceladus ocean. So the water chemistry, this means the moderate alkaline pH and the high CO2 concentration in Enceladus and other ocean worlds beyond the CO2 snow line is suitable to achieve the high phosphate concentration in the subsurface ocean. And the Enceladus could provide insight into the potential aqueous environment for the emergence of Earth life, especially for the phosphate-induced chemistry. So there are several open questions remaining for Enceladus. The one is whether the high concentration of phosphate can be involved in the chemical evolution on Enceladus. And another open question is if life exists in Enceladus, the question is why abundance of nutrients and also chemical energy left over. So if life exists in Enceladus or as a location, the life should consume almost all of the available nutrients or chemical energy. So why the abundance of nutrients and chemical energy left over in Enceladus is one of the major questions. The one possibility is, of course, the Enceladus is lifeless satellite. And another possibility could be the life in Enceladus has long turnover time for the metabolic reaction. So these open questions could be a major science goal for future mission to answer this. So that's all for today. Thank you very much.
Thank you very much, Yas, for the wonderful and very thoughtful talk. So let's move on to our Q&A and the discussion part. So if anyone has a question or comments, please raise your hand on the Zoom function or just type your question onto the chat box. Either way, it's fine. And while people are thinking questions, I would like to ask my question. So the carbonaceous chondrites are the product of the aqueous alteration, the parent body. So based on your result, do you think that we should find the decline trend of the phosphate abundance with the alteration degree as a supporting evidence for your model?
I still don't understand the question, but so the question is yes.
Yeah, my question is that because the carbonaceous chondrite is a product of the water rock interaction within the parent bodies,
Yes.
the potential phosphate loss to the aqueous part would result in the decline of the phosphorus abundance in the rocky part. So if we find some decline trend of the phosphorus abundance in the carbonaceous chondrite, that could be some supporting evidence for your model.
Yeah, but the phosphate concentration, I mean, in the water part, the total abundance of phosphate in water parts is probably much smaller than the rocky part. So even if the dissolution occurs effectively in some rock materials, I mean, in some chondrite materials, but the total abundance of phosphates is much higher than the phosphate dissolved in the fluid material. So I think that it's really hard to quantitatively compare the dissolution efficiency.
Okay, thank you very much. So any questions, comments? One question from Robin on the chat box. How important do you think the role of more reduced phosphorus compounds in Enceladus chemistry could be?
Yeah, in the meteorites, the reduced phosphorus compounds are found, like phosphorus combined with iron or nickel are found in the carbonaceous and other chondritic materials. But according to the previous studies, those reduced phosphate compounds is easily converted into phosphates in the reaction with liquid water. So even if the reduced phosphorus compound contained in rock materials in Enceladus, that easily converted into the phosphates in the reaction with liquid water.
Yes, thank you. Or any other questions, comments from audience? You can just raise your hand or type in to the chat box. Another question I'd like to ask is about your open question part. So you suggest one of the future study is to predict the limiting factor for life within the Enceladus ocean. So if phosphorus is so abundant, do you suggest possibly the nitrogen could be the limiting factor, or do you suggest that even the energy could be the limiting factor? Can we somehow predict which element can be the limiting factor for the Enceladus ocean?
Yeah, the nitrogen is also abundant in Enceladus ocean. According to the Cassini observation, about the 1% of ammonia is included in Enceladus ocean. So the availability of nitrogen is also very high in Enceladus. And the chemical energy is also abundant. The H2 hydrogen is about 1% and the CO2 is almost 1%. So the available energy is much higher than or almost comparable to Earth's hydrothermal system. So no energy limitation, no phosphorus limitation, and no nitrogen limitation. So one possibility of the element that can limit the Enceladus Enceladus life is the availability of nickel. The nickel is how do you say, the central elements of cofactor of methanogen. So all methanogen on Earth use nickel. However, the nickel availability becomes very low in alkaline condition because the nickel is distributed in the rocky parts in the alkaline pH condition. So the one possibility is the very, very low abundance of nickel in Enceladus could limit the activity of methanogen. So in that case, the question is whether the nickel is the ubiquitous elements that used for the methanogen. And interestingly, the fission-trophic catalysis, abiotic methane production, producing catalysis always use the nickel. Nickel is the most efficient catalyst for methane producing catalytic reaction. So if the nickel is ubiquitous elements that promotes the methane production, then the nickel could be the limiting factor of Enceladus life.
Thank you very much. And there is another question on the chat box from Gisupe. So if a wet-dry cycle is needed to forming nucleotides, how could they form on Enceladus?
Yeah, this is really interesting question. So in the wet-dry cycle, the nucleotide can be formed because of the decrease in the water activity. So the water activity decrease, then the phosphate can be incorporated into the organic materials. So the similar decrease or almost zero water activity could be achieved in Enceladus within the icy shell. So Enceladus, the icy shell is always recycling. The ice materials dissolved and the ocean materials are incorporated into the ice. So if the organic materials together with dissolved phosphate and entrapped within the icy crust, and then this icy crust are, convecting and slowly freezing, then the water activity of water would be very low or even become zero. Then the dissolved organic material and the phosphate could be, the phosphate can be incorporated into the organic materials. So the freeze-thaw cycle could be similar to wet-dry cycle. But now we are doing this type of experiment, but we still do not have a result. So we are looking forward to seeing the results for the phosphate incorporation into the organic materials through, freeze-thaw cycle.
Yes, thank you very much. So does anyone has any other questions, comments? So I'd like to shift a bit more to the discussion on the rocky worlds from the IC worlds. And so yes, you actually have already discussed lots of the implications for the early Earth. But do you see that the difference on the rocky composition, like the carbonaceous chondrite versus more earth crust like rocky composition influence the resulting the phosphorus abundance a lot? I'm not sure if you have included that difference into the estimation or not.
Yeah, I agree that the rock composition strongly affects the results. So if we have mafic or ultramafic rock component, like chondritic materials or the deep crust materials, like the presence of olivine or pyroxene in the rock materials, then the fluid pH of fluids that interacted with such ultramafic rock composition becomes the alkaline. On the other hand, the more silicic rock, like a granite or other silica-rich rock materials, then the pH of the fluids that interacted with those rocks becomes around the circumneutral pH or even acidic pH condition. So in generally, if we have mafic or ultramafic rock materials, then the pH becomes high or super high. So in order to achieve the pH around 9 to 10, the mafic rock materials is required.
How about the influence of the difference in the phosphorus abundance itself? I heard that the crust is relatively rich in the phosphorus, so it could help more higher abundance to produce more higher abundance. Yeah.
Yeah, granite. Yeah, actually, the as Hiro said, the granite. Granitic rock contain more apatite. However, even in the reaction with the water, and the water pH is acidic or circumneutral, then the apatite dissolution is really low, or the most of the phosphate is, distributed in the rocky phase. So even if the rock contains the phosphate, the granitic rock generates the acidic pH or circumneutral pH, then the phosphate cannot dissolve into the fluid phase. And if we have mafic rock materials like comatiite or basalt, those materials contain less phosphate in rock materials, but the pH of fluids that interacted with those rocks becomes alkaline. So then the phosphate can be easily dissolved into the fluid phase.
Okay, thank you very much. I think we are close to the closing time, but I think we could have one or two more additional questions. So if you have any questions or comments, just raise your hand or type into the chat box. If not, I'd like to close today's discussion. So yes, thank you very much for the wonderful talk.
Thank you very much.
So this gonna be the end of today's discussion, and the next Rocky Worlds discussion will be held on the Thursday, March 2nd, from 1 p.m. UTC. The speaker is the Lars Butchev from the Technical University of Denmark, and the topic is about the detection, the characterization of the terrestrial exoplanets. And I'm looking forward to see all of you again there in a month. So thank you all for joining today, and see you. Bye.
Thanks, everyone. Thanks, Yasu and Hiro. See you soon.